So we have a few different paradigms for linear systems. To summarize what we know so far, let's revert back to our model linear system. The first way of thinking about this problem is as a linear combination problem. We've worked this out before by factoring out the x and the y terms to get the following, so I'm just going to write it down here. The second way is to write this as an augmented matrix, which we've used a ton to solve linear systems. Now in this video, we're going to look at a third way called matrix equations. So how do we do this? Well, let's start by taking down the coefficient matrix. And we've seen this before. It's just the coefficients of the variables of the linear system, and in fact, it's the left part of the augmented matrix. Let's take x to be the 2x1 vector of variables, and b is going to be the 2x1 vector of constant terms. So we're going to take a look at the equation ax equals b, and you should take a second to convince yourselves that the dimensions all match up nicely. And let's apply matrix multiplication to the left-hand side, ax. If we expand this like we've practiced, we'll get this, which we note lines up perfectly with our original linear system. So if we set it equal to our vector of constants, then we get an equality of two vectors which corresponds exactly to the linear system. More generally, if A is an m by n matrix of coefficients, x is an n by 1 vector of variables, and b is an m by 1 vector of constants, then the matrix equation ax equals b corresponds to a linear system of m equations in n unknowns. And on the flip side, every linear system can be written in this way by emulating that process we did above of extracting the coefficient matrix and the variables. So this is our third model of a linear system, and it's going to greatly enhance our ability to study such systems.